our weekly seminar series at UKZN. It gives me great pleasure to introduce our speaker today. Can the online speakers, participants confirm that you can indeed hear us?
Yes, yes, we can.
Thank you so much. So today I have great pleasure in introducing Dr. Heba Abdulrahman. Heba grew up in Egypt, and she had completed her BSc in physics at the University of Cairo. She had told me in confidence, but I'm going to divulge some information now, that she did not go to the mathematics department because she was afraid of the mathematicians there because they usually show up in pajamas at the maths department at Cairo University. So that is how she ended up in physics. But nonetheless, she then completed her honors in physics, and in 2015, she went to Ames, Ghana, where she then fell in love with cosmology. Following that, in 2017, she came to South Africa, where she completed her master's in Northwest University, so at NWU. Following that, she of course completed her PhD at NWU, and now she is at UKZN as a postdoctoral research fellow. Apart from her academic achievements, Heba is well known for her cooking and her baking skills. I mean, Shop Maharaj can attest to the wonderful cookies that we often get at tea. She's taken up a few other hobbies such as crocheting, which she started recently. She said she's doing that to relieve some of the stress during her postdoc. Heba, we're really looking forward to your talk.
Thank you so much. Good afternoon, everyone. So first, I would love to thank everyone in general, and I'd like to thank Professor Shamil and the University of KwaZulu-Natal and the NITheCS for allowing me, for giving me this opportunity to share some of my research work with you today. So today I'm going to talk about unifying the background with perturbation in Chaplygin-gas. Before that, can you please allow me to share some pictures of my own country, Egypt? So as Siri mentioned, I was actually born and raised in Egypt, in Cairo. So Cairo is actually one of the oldest inhabited cities in the world, and it's also considered to be one of the most crowded and one of the most noisy and busy places. But unfortunately, it's a package. You take it all or you leave it. So the word Cairo, it's actually derived from the Arabic word Al-Qahira, which means the victorious. So over there, you can see this is one of my favorite places in Cairo. So whenever I get the chance to go and visit Egypt, this is the first place I visit. This is Coronation Nile, or the Nile River. So I always go and for a Tanuka ride along the Nile River just to enjoy this beautiful view. And down there, this is also one of my favorite spots in Egypt, where I having a walk. This is downtown Cairo. So this is like 15 minutes away from where I stay in Egypt. So I took this picture actually during my last visit in Egypt in April. And to get this picture, I had to leave the house around 5 a.m. in the morning. Otherwise, you cannot stay in this area after 7 a.m. So here, this is like the Cairo University. This is where I did my undergrad and my honor degree. And I joined the physics department at the Faculty of Science in Cairo University. And as Siri mentioned, I ran away from the mathematics department because I was really scared of just going to the work with tangled hair or wearing my pajamas. So before I chose to work on gravity and cosmology, I was very fascinated with nuclear physics and high energy physics, elementary particle physics, but I changed my mind after I joined the African Institute for Mathematical Sciences. So if you look at this picture here, this is actually my best friend. It's my comfort zone during my study at the university. So if you know the nature of the Faculty of Science, in Cairo. So you will know that we used to start classes from like 7 or 8 in the morning and we finish around 8 p.m. in the evening. And writing exams, sometimes we used to write exams like after 9 p.m., sometimes after 10 p.m. So I never got the chance like to explore this campus. And I was like I've stayed there for like 5 or 6 years. How come I couldn't get like to explore this campus? But this place here was my comfort zone. This tree is like actually as old as Cairo, like since Egypt, like Egypt is actually full of old stuff. So this tree here is actually older than the Cairo University itself. It is called, as far as I remember, it's Tango Dragon tree. So this tree was like my comfort zone. As I said, I used to sit under this tree, study and eat, and sometimes like planning for our lessons. So back to science. So over there, the outlines my talk. So first, I'm just going to start by giving a brief review over the gravitational, or the history of the gravitational theory. So I have been always thinking about the history of the gravitational theory. See, when we talk about it, I've been always like fascinated about the concept of gravity, especially since it is something that we actually experience like every second. Also, because it's also like a very complicated or a very complex phenomena as well. So since I'm also fond of like history and philosophy, so learning about like the history of gravity has actually allowed me to like accept like the world around me more, like, to appreciate the world around me more. So because it is actually something natural, like almost every single human being from the very beginning and every single civilization were questioning about like, the origin of the universe or the origin of the creation. So today I'm just going to like mention a few because the list is very long. So I'm going to start by the ancient time. So in particular, like one of the ancient Greek philosopher, Aristotle. And actually, when I was young, I used to think of Aristotle as that was my favorite bit. I'm sorry. So Aristotle actually he was the first to like propose like a theory about gravity. He didn't even notice or realize that he was talking about gravity. So he actually proposed that like all the objects like will fall like eventually on the earth or on the ground because they are seeking like their natural like places. And he also believed that heavier objects will fall faster than lighter objects. And this was followed by the medieval era. So this era was actually full of like a lot of scientists and a lot of philosophers. But for me, I'm actually fond of this John Columbus. Like apart from the fact that they consider him as a Greek philosopher, but he was actually born and raised and died in Egypt. So he's Egyptian. So this guy here, he also talked about the theory of gravity when he assumed that the speed of the falling objects actually depend on the weights. And there's something that I need to mention here about like the history of the gravitational theory, especially before the 17th century. At that time, like people actually related, like we were talking about more about the planetary movement or the planetary motion more than gravity, because at that time they actually believed that the Earth is the center of the universe. But after that, everything changed with the beginning of the scientific experiments during the 17th century, when Kepler and Galileo were able to explore or observe the planetary movement. So, and this is actually later, because of this discovery, allowed Newton to explain the gravity by introducing Newton's universal law of gravitation. So according to Newtonian theory of gravity, gravity is a force, okay? And this force is actually, like you see, like if you have like two masses in the universe, these two masses will attract each other because of this, which is directly proportional to these two masses. So Newtonian gravity was able to explain the motion of the planets, but it also had some problems. Like, for instance, the idea of absolute speed and absolute. So according to the Newtonian theory of gravity, so the space and the time, they were thought to be independent from the reference frame. But the most important thing about the Newtonian theory of gravity is that this theory is only applicable or limited to like non-relativistic phenomena, like or weak gravitational fields and those things. So we think, okay, I'm not going to talk about what it is. But what can I know in this? What's short?
Yeah, it just
So in actually order to cover this issue of like how big and big gravitational field, later in 1905, Einstein chose theory of actually a generalization of this I actually extended including like accelerated frames. So if we look at this equation here, according to Einstein, he actually described gravity as like a curvature of the space-time. So gravity, according to Einstein, is not a force. So he assumed that the space is a four-dimension and he called it space-time. And according to this equation here, from equation 1, we can see that this is actually the Einstein field equation. So the first term here is the Einstein principle, which actually describe the geometry of the space-time. And the second term here, and this is the gravitational field, which is actually responsible for mediating the gravitational interaction. And this term also the energy. So by looking at this equation, you can clearly see that here, this term here, which describes the gravitational field, is actually attached, like connected to the geometry of the space-time, and it's also matter and the energy pointing to how. So from this equation, Einstein was able to explain or to predict the gravitational waves. He was also able to give like an explanation or about the behavior of the black holes. But the problem arises when he tried to apply these field equations to the universe at very large scales and at very small scales. We found that these equations can only work or cannot work for like a static universe. So the universe has to be expanding or contracting. So in order to solve these problems, he added this extra term in these field equations, the cosmological constant term, just to avoid the gravitational effect of the gravity. But later, in 1922, Friedman funded this assumption when he managed to obtain a cosmological solution to Einstein field equation. And from the solution, he actually found out that the universe is actually the universe is expanding. So this is the solution of the Friedman equation. So the first equation here actually representing the velocity of the expansion. In here, it's easy. Hence, the amount of the matter in our universe. Temperature. Actually, the behavior of this equation changed depending on term here. So okay, like for example, for the case when k equal to 0, this is a like flat universe. For the case when k equals to 1, This is an open closed universe. As I remember, no? Always confused. Yeah, and for the case when k is negative, this is an open universe. So actually, as I said, the behavior of this equation here is like depending on whatever we choose for our curvature. So this equation can end up like having like forever expanding universe or a universe that collapse. And the second equation representing the acceleration of the expansion. So these frequent equations were actually also consistent with this experiment, like in 1929, when Edwin Hubble showed that the universe is not in fact static. He managed from his experiment to show that the galaxies are actually moving away from us with a distance proportional to their distance. So based on the Friedman equation and this experiment, they actually formed the basis of the standard model of cosmology. When we talk about cosmology, cosmology is the study of the larger scale structure, the origin of our universe, and the evolution of our universe. So this diagram here, I'm sure all of you are familiar with it. So it shows the evolution of the universe. It shows like different stages or different. So according to the Big Bang theory, so the universe at like very early time started as a very tiny ball, and then followed by the initiation era, like when the size of the universe started to increase. After that, we came to the recombination era when like, the photons and the electrons started from hydrogen atoms. After that, when the universe started to cool down and releasing, and these hydrogen atoms started like to reach to its first like energy state and starting to release some photons. This is when we get the cosmic microwave background. After that, we can clearly see the formation of a large scale structure, the formation of the structure. But we can teach that it's managed to find the origin of the cosmic microwave and also managed the formation of the large scale structure. But okay, so before I proceed, I need to mention here just in order to explain these different levels of the universe, we introduced this equation here, equation 5, which is actually the equation of and this is the isotope equation, and this is the equation of and this is the equation. Just in order to describe the difference. Minus 1 for the equation. So I don't actually want to call it shortcomings of the standard model of cosmology or because last time I discussed with Professor Hito, he told me like what problems? There's no problems. So I figured out it's actually like maybe it is we should call it the shortcomings of our understanding to the standard model of cosmology. So according to the standard model of cosmology, as I said, it's managed to like explain the origin of the cosmic microwave background, the formation of the largest scale structure. But the problem here is that, okay, I see the problem again. So it's the accelerated expansion in the present universe. So according to the observation, our universe is accelerating, and we cannot explain this wave cosmic acceleration. Besides that, also the dark matter and the dark energy problems again. So like so this unknown form of energy like almost represent like 70% of the matter energy content our universe, and is also believed to be responsible for the accelerated expansion in our present universe. But we cannot actually define and explain the nature of this energy. Another problem, another shortcoming, is the homogeneous. I need to get used to it. So last week I was introducing it as problems. Actually, yes, you were right, it's no problems. So another shortcoming of our understanding to the universe is the homogeneous and isotropic universe. So this is the cosmic microwave background. as I showed earlier. So this is like the leftover radiation from the video. So according to the cosmic microwave background, at the large scale structure, our universe looks homogeneous and nice. When I mean what I mean by homogeneous or dimensional space, right? And isotropic. But this is not the case. Let's imagine we are having a small portion. Okay. So we can clearly see this now for university homogeneous and is anisotropic. So we could not find an explanation for this. So like there were like many suggested like solution or maybe ways to try to figure out or to find an explanation for these issues. So one of which is a modified gravity, which one of my colleagues consider it as a rubbish theory, but it's fine. So
I think you're being unfair. Didn't say about gravity charge. Say most.
it's about timing, Professor.
It might be some of them are okay. Others,
Yeah, it's not about timing. Yeah, it's not about. Yeah, it's okay. No, it's fine. So when we talk about like modifying gravity, it's actually trying to find a way to deviate from the general theory of relativity. So if I want to go back to this equation here. So by looking at the field equation, Einstein field equation here, I mentioned that this term here like represents the gravitational field that is responsible or mediating the gravitational interaction. So when we think about modifying gravity, so what if we add actually extra gravitational field beside this field? So we have like more fields to mediate the gravitational interaction. So this is actually the idea of some of the modified theories of gravity, because not all of them adding like extra gravitational field. Like for the past 5 years, for example, I have been working on FFR theories of gravity by adding higher order dimension, Einstein reflection. And I've been also working on the scalar tensor theories of gravity, gravitational scalar tensor theories of gravity, and also FFT gravity. FFT gravity is actually a generalization of the teleparallel gravity. A teleparallel gravity is just, it's like another way to describe the general theory of gravity using like a different geometry. And of course, the higher dimension, that HB theories. So this is just a way of trying to find like an alternative to the general theory of relativity to just try to address some of these shortcomings of our understanding of the standard model. But today I'm going to talk about Chaplygin-gas. The talk is about unifying and the background and perturbation in the Chaplygin-gas. So Chaplygin-gas actually is a hypothetical. It's actually believed to behave like dark matter in early universe and dark energy. So from now on, I'm just going to divide my talk to 3 parts, just for everyone to be in. So the first part of my talk will cover the background cosmology. So here, this is the first model I have. It's a generalized Chaplygin-gas model. So from equation 7, we can see the negative pressure associated with the generalized Chaplygin-gas is related to the energy density. So this equation of state, where A and alpha here are constant. So for the case when alpha is greater than 0 and less than or equal to 1, this is the generalized Chaplygin-gas. And for the case when alpha is equal to 1, this is the original. In equation here, equation 8, I define the conservation equation. So here we define the energy density of the multi-fluid universe. So we are assuming that the universe is consisting of Chaplygin-gas and ionic matter. But for instance, like if we just try to think about it, like if our universe is actually dominated only by Chaplygin-gas. So if we try to solve this equation for the energy density, we can clearly see how the energy density will evolve for different levels of the universe. So by solving equation 8 for the energy density by considering only Chaplygin-gas, we get equation 9, which is the energy density of the Chaplygin-gas. For C2 here, it's just about the constant. So I want you to look at this equation. So now we're just going to assume some limiting case for this equation. We're going to assume the case of early universe. The scale factor is very small. So for this case, C2 over A will be much bigger than this term here. And if we assume like the original Chaplygin-gas model means alpha equals 1, we will end up having rho Chaplygin equals this expression here, which is actually similar to the burst and the bulk model. So we can easily see that Chaplygin-gas can be interpreted as ionic-like model. And on the other hand, if we assume a negative sign, scale factor big. So when we have here C2 over A much smaller than this, we are assuming also the Chaplygin-gas will up. We will end up having rho Chaplygin equals constant in the future universe. We can integrate that as Chaplygin, like our universe is like as if we are having an empty universe with a cosmological constant. So now I introduce equation 10 here. So now I assume a universe that's consisting of Chaplygin-gas and ionic. So from now on, I'm just going to shift or change the variables from the scale factor to the redshift, because the redshift is actually a physically measurable quantity. So after doing that, I can get the Friedmann equation from equation 10 as presented in equation 10. And by dividing this Friedmann equation by 3h naught squared, we can get the normalized Hubble parameter as presented in equation 10, where h naught here is actually like the value of the Hubble parameter, and here we find fractional ordering the dimensionless parameter. And we also define the fractional parameter. Actually assume that universe. So now the main target of this part is we're trying to explain like the expansion or the rate cosmic expansion of the universe. Okay, but like when we are like including or assuming challenges. So in order to do that, we are going to do like some further analysis. So we are going to analyze some cosmological constraints, like for example, the deceleration parameter. So we're going to constrain these parameters, and just in order to like we are looking for the most like or the best model of the Chaplygin-gas. So we're going to do that by using the MCMC simulation. So we'll be using the MCMC simulation just to basically parameters. So what we're going to do here, we're going to insert the Friedmann equation of lambda sphere and the Friedmann equation for different Chaplygin-gas models in this equation here, the distance models, and we're going to calculate or finding the best fitting parameters for Chaplygin-gas models. So after doing that, so I managed to get the deceleration parameter for the original Chaplygin-gas and generalized Chaplygin-gas as presented in. So by looking at this equation, so this equation now we constrain the parameters by the parameters that we constrain just alpha, consider like the next constant. So we put the numerical like solution for this deceleration parameter as presented in equation 1 and equation 2. Equation 1 is for the case when the original Chaplygin-gas when alpha is when finding the original Chaplygin-gas. Second, both represent the generalized Chaplygin-gas is then 1. And you can clearly see that the results are actually consistent with what we expect, like the expansion or the accelerated expansion of the universe. You can see that the transition from the deceleration is greater than 0 to the acceleration in Q is less than 0. The second model that we have is the modified Chaplygin-gas model, given by equation 16. So this model, like A and B are just constant. So for the case when A equals 0, this is actually reduced to the equation of state with the perfect model. And for the case when B equals 0, this equation of state reduces to the equation of state. So similarly to what I have done in the previous model, I'm the constant present numerical expressions. So here, for different values of the same here for different values. It's just one. The last model that we have, modified visualization. So I don't want to take a lot of time in this. So similarly to what we have done, we have also calculated deceleration parameter and we presented the numerical results for the deceleration parameter, and we can still see like model number 4 is the extended Chaplygin-gas model, given by the equation of state presented in equation 18. So this model is actually an extension of the modified Chaplygin-gas model and the modified generalized Chaplygin. As we can see, included so what we have done here, we have actually expanded the single notation here in equation 18 to this. And we also managed to minimize the counter and the deceleration counter. As you can see here, the last model that we have is the equation of state. Sorry, it's a generalized cosmic Chaplygin-gas model. So I'm just not going to waste time here. So similarly to what we have done, we have also numerical results for solution parameter. And this model is actually rolled out completely. So as a summary of one of one, so we find out that the extended Chaplygin-gas model is put out in the early literacy. Generalized Chaplygin-gas model is put out. Okay, background. So the second part of my talk. So the second part of my talk is just covering the supernova cosmology for different Chaplygin-gas model. I'm just going to go through this quickly. So we are just using the theoretical results. So we're just going to compare the theoretical distance model with the theoretical simulation. Actual data with actual supernova data is better than this. I'm just going to go through it. Okay, let me just go to the results. I actually here tried since we use the MCMC simulation to find the best fitting parameters for each model. So what we have done here, we tried to plot these best fitting parameters with the supernova. So I'm just going to go through this is just the results, all the results actually you can see it's actually perfectly perfect with the supernova data, but But this is not enough. Like what we have done here is we have done that we used some statistical analysis on the best fitting, what we have done here, we tried because we compared the models with the lumpicity M. So we wanted to know like whether we left some models behind or whether we left some information behind. That is why we applied the statistical analysis. So based on the statistical analysis, we use the Jeffrey scale range. So I'm just going to go through this table. So according to the Jeffrey scales range and according to our statistical analysis, you can see that the original Chaplygin-gas model is actually showing like more observational support. Plus, the generalized Chaplygin-gas model is so from like a summary for what two of my talk, you can clearly see that the original Chaplygin-gas model, generalized Chaplygin-gas, extended Chaplygin-gas model showed more observations. The last part of my talk is just we're trying to study the contribution of the Chaplygin-gas in the formation of the largest scale structure. So I'm just going to go through the results since I don't have time. So we are going to study the contribution of the Chaplygin-gas for in the formation of the large scale structure. Since I mentioned at the background only the original Chaplygin-gas model and the generalized Chaplygin-gas model and modified Chaplygin-gas model, we're working at the level of the background, and at the level like the actual data, the OCG and the GCG and the extended Chaplygin-gas model. So at the level of the perturbation, we're defining this perturbation variable here. This is representing the density perturbation for the modular density perturbation, and this is representing the volume expansion. And this term here represents Chaplygin density perturbation, and the last term is for the total, like including the baryonic matter and the Chaplygin. So we take the time evolution of this equation, and we get the second order evolution equation, or the second order equation, and we were trying to solve. So what we have done here, this is the generalized form of the perturbation equation without specifying any Chaplygin-gas model. So at the perturbation level, we actually choose to study the original Chaplygin-gas model and the generalized Chaplygin-gas model and the extended Chaplygin-gas model to show some. But first, I had to like find the solution, find the GR solution, and one XCD solution. So here, what we have done, this is the perturbation equation for the GR, and this is the equation for the so I'm going quickly to visual Chaplygin-gas model and visual Chaplygin. Just so we can clearly see that according to and clearly see the most matter, and the family. But for the last model, which is NCC, you can actually see that you cannot see everything. So as a summary for this part, the OCG and GCG working perfectly at the background level, working perfectly compared to observation, working perfectly at the perturbation. I'm not sure if I have time to go through. Yeah, so as I said, we studied the background cosmological, background level, observation level, and perturbation level. So as I said, I'm glad I did a summary for each part. So as I said, the OCG and the GCG working perfectly at the background and like they showed like some observational like promising results, and also they working perfectly at the level of perturbation. And I think I wasn't expecting to get this much time. Yeah, I just wanted to end my talk with one of my favorite ancient Egyptian proverbs. It's written on the walls of Amon's temple. It is like, know the word in yourself, never look for yourself in the world. Project your illusion. So it's always important to receive the benefit.
So thank you very much for that, Bella. So Sabine and I decided to share to make the introduction.
And you're going to be the chair.
And most unusually, she's offering the last word, which is
It's always
my last word. So thank you for that. And questions, comments? Well, the warming up the questions, I'm sure there are lots of questions. I just wanted to, when you spoke about the perturbations and the was consistent, but other perturbations is lead to a model which is stable. Is a model stable?
the models next, yes, for the oxygen model and the generation.
Yes.
So you presented a couple of models and
Yeah.
so according to you, so then you would say the original Chaplygin-gas model and the general one are best there, and does that mean the others are unstable, or say what?
No, the reason why like the OCG and the GCG are the most stable, I think it's because like the more we increase the number of the pre-parameters, the more like or the less the model will be stable. That's why we have done this statistical analysis. I did answer the question.
Yes.
Yeah.
Anything else? This is about to one.
Well, as a novelist,
Oh,
so
oh, I actually like I
models is come from regional here.
yeah, we were trying to find
Excellent.
yeah, we were trying to find a model that can give us an explanation. Without actually
There are certain observations. Standard. So when one talks about shortcomings, they would agree with the space one that that's one word to use.
yeah,
Because you have a theory, you build a model.
yeah,
And the model, you try to relate that observation. The model is never complete. Then something will come along, give an observation, try to accommodate that observation somewhere. So the model is ever changing. It has to be, it has to be that way. And not only a model, but I would say a theory.
Yeah.
Because Newtonian theory, which is GR, that's everything else. So it's not a weakness of the model.
it's the weakness.
Yes, yes.
So that's why I'm trying to find the alternative for shortcomings.
One thing is that you put the slide with all the various types of theories,
Yeah.
modified reality, in the center. So each one of them has certain language shortcomings.
Yeah.
Any language shortcomings in some way or other. But it's the other thing to do is out of that, some insight comes.
Yeah,
That's
this is
something that can be used in building something more accurate as we go along.
that's what I was told by Ernest. It's always nice to explore because this is research.
Yes, but some things are inconsistent. There is
Yeah,
If
how can we tell?
if one of those, I must say which one, if one of them tells you, for example, that the getting models of the ACOS, then that can never really represent.
Yeah, but I will
So,
ask you a question. How can you tell if some of them are inconsistent? They don't actually speak?
yes, yes.
Yeah.
You can only make that statement after.
Exactly. Yeah.
Any further questions? No, there's nothing, there's nothing. No, there's nothing.
Oh, yeah.
So normally they send the questions, so,
Yeah.
so there isn't anything online. So thank you everyone. Thank you for the online attendees.
Yeah, thank you so much.
And thank you, Heba, for taking great care in creating a talk which gives background and also aims people who are not precisely working on this problem. It's very, very easy to just sit down and engage in what you're working on, talking about that. So the only person who can understand you is that.
Oh,
So this is quite nice. It's general. This is what these type of seminars are designed.
yeah, but unfortunately, I didn't have time to like the actual work.
But you were told you had 35 minutes.
Yeah, I didn't realize that I spent the 45 minutes. I mean, I took like
In that case, we can arrange another seminar.
yeah, I don't mind.
We'll see.
I was just going so fast. Thank you.
No, it was good. We got a flavor for what was intended. So thank you very much. So just thank.